Hi, everyone. Thanks for having me today. My name is Ryadh. I work for ClickHouse. Very happy to be here today. I know it's always tricky to be the session right after lunch, so sorry if I'm waking up some people, but I hope that will keep you entertained by running a lot of demos. So actually, preparing this talk, I removed a lot of the slides to keep, you'll see maybe 4 or 5 slides, and most of it will be like a long-running demo. I hope that we will just display how these things are implemented in ClickHouse, how they work, and what we use them for. Before I start, just a quick question. Who here in the room hasn't heard of ClickHouse before this talk? We have 2, that's cool. So ClickHouse is basically open source OLAP database. So if you think of like Postgres as kind of the established OLTP database out there in the open source space, ClickHouse is the equivalent for OLAP. It has been widely successful, widely adopted for many years. It was open sourced back in 2016, so 8 years ago, and it had a wide adoption pattern. People love using ClickHouse for analytics use cases, and the fact that it's open source means that it evolved basically by contributions, by user needs, by actual use cases versus like a pre-planned agenda of features that people thought about. So it kind of organically grew into a fully-fledged OLAP data store. Fairly popular open source project, as I said, and it has few secrets under its sleeves. It's, first of all, as any good OLAP database, it's column oriented to benefit from locality effects and things like that. It has a vectorized query engine that runs CMD instructions, so that can be pretty fast and utilize every core of your computer. Try to display that. It's good for running aggregations, obviously, but it's also a distributed one, so you can run unit in a cluster if you want. You can do replication, sharding. It doesn't have a notion of master. It uses Keeper underneath, but Zookeeper initially, now its own implementation, what we call ClickHouse Keeper. And people use it for many things. Like an OLAP database, as you can imagine, has many applications. For ClickHouse, mostly around the real-time analytics use case. By real-time analytics, we mean basically managing continuous streams of events and answering questions on top of these events, but also other things like people use it for user-facing analytics, like when you have analytics capabilities in your app, when you're using your bank account app or your Uber Eats or any of these like modern analytics experiences that are baked into our everyday lives. That's a very prominent use case. People use it as a vector store because it has vector storing capabilities, or use it for observability, which is, I think, in my opinion, it is a subset of real-time analytics that's dealing with machine-generated data, and it has been very popular in that space. That's actually maybe our biggest use cases are in that space because it's unbeatable performance and cost. But as I said in the intro of this slide, I won't talk too much. I'll try to display basically these aspects. We are in the Polystore workshop, and preparing this talk, I was basically browsing around, and the web page basically describes 4 dimensions here of what the Polystore provides, like discoverability, integration, cleaning capabilities, and efficient access. I thought it would be pretty cool if we can orient our demo towards this. So we can have a hands-on experience and display basically that we achieve that using ClickHouse. So it's very easy to install ClickHouse. You just run a curl command against our website. Thanks to user agent detection and some magic that happens inside this script, we download the right binary for your architecture, and let's do it. So I have a terminal here. Actually, downloaded it because I haven't trusted the network before, but you can just run the curl command if you want, and conferences networks are not always reliable. There's 3 different ways to run ClickHouse. One is what we call ClickHouse Local, and in that mode, basically, it's an in-memory OLAP database. You run anything you want inside this in-memory database. You can run aggregation queries. Let's say, I don't know, let's select numbers from the numbers function in ClickHouse, which returns basically a sequence of numbers. And in that case, it stays inside your context, think of it as a kind of your DuckDB or your like tooling for ad hoc analysis. It's pretty cool because you can read any format, export to any format. So by just simply tweaking your query, let's print some pretty JSON each row here. If I'm happy with that, I can export it to an out file, and then imagine that with like a huge Parquet file you need to transform for another analysis. Imagine that with projections, aggregations, anything you want to prepare your data set. So ClickHouse Local is for this use case. Let me start now the fully-fledged experience of ClickHouse server. So in that case, it's a database server. So it starts and it's ready for connections and start accepting connections. So what do we need to connect? We need a client. Let me find my binary here. Just be around here. And we ship the client within the same binary. That's very handy. So starting ClickHouse client, we give me a prompt into my server. Locally, everything works straightforward. But let's start with a demonstration of how fast ClickHouse can be. So I'm running everything on this MacBook M1 MacBook Pro from 2 years ago. Let's create a very simple table with an ID, that's a sequential number, and X, which is a value. Let me insert 1 billion, let's say, to start with. 1 billion rows into that table. The ID is sequential, and the X value is a random number. So let's see how long it takes to insert 1 billion rows here. Oh, it's not 1 billion, I made a mistake. It's 100 million. Let me do it again. I said 1 billion, so let's not deceive people. I need to truncate it. And let's add a 0. Yeah, so we do about 80 million rows a second on my M1 laptop. Again, it's not that bad. Writing data to disk. All right, it's in there. Let's see if I already have my 1 billion rows. There's a handy function called format readable quantity, which basically prints human readable formats. And yes, that's 1 billion rows. That's all right. What it looks like. It looks like random numbers associated with IDs. So that's what I wanted. All right, let's run now a more useful query. Well, it's not really useful, but it's useful to display how fast it can be. Let's run a sum over this table, a sum of all the random values generated. And let's see how long it takes. All right, less than 1 second for 2,000 quadrillions. That's not that bad. And again, all of that is happening on my disk locally. And I can show you basically how we structure data on disk without going into many details. This is reading system tables. To display that, we split the files into what we call parts. We have a sparse index on top of it. We can skip pretty efficiently data. We compress data very efficiently. Not in that case, because these are random generated numbers, but usually if you deal with user-generated data or machine-generated data, that's pretty convenient. And here we have 11 compact parts that contains about 1 million rows each, etc., etc. So that's just for kind of the show. It's a kind of a nice icebreaker exercise. Yeah.
Can I ask a question? So how is the number of parts determined?
By default, there's a regular interval that's 8,192. That's set by default, but this is also something you can tweak when you create your table. You decide basically on this like hop. It's called the index granularity in ClickHouse, and you can define it.
So what type of index do you create, at the beginning when you insert like the numbers?
Yeah,
What's
so
the default index?
the default index is a sparse linear index, and it uses a very confusing name, which is called the primary key in ClickHouse, which, because it's a database concept, sometimes confuses people, and that's a habit in ClickHouse. You see later that materialized view in ClickHouse are also a different concept than materialized views. That's just naming conventions, I guess. But yeah, it's a sparse index, it's a skipping index. There's a default version of it, but then you can add secondary ones, like Bloom filters, anything you can think of can be also applied as a secondary skipping index. Yeah, another question here.
Sorry, did you say there's 11 parts and each has 1 million rows?
Apparently here, yeah. No, sorry, I was reading the last parts that were basically the remaining. Yeah, that's a good catch, actually. Now here I have some with 200 million, some with 37, yeah. That's a good catch. Thanks for that. All right, let's see here what we do. All right, workshop is about polystores, discovering data on various systems, interacting with heterogeneous systems, and let's see how we do that. Well, you need two things to interact with other systems. You need to be able to talk to them, so you need like kind of client capabilities baked in your data store, which is not exclusively kind of the core database concept that a database is shipped with, but it's a nice extension to have within the same tool with the ability to talk to many things. And in ClickHouse, this is called table engines or table functions, depending if you want to initiate it as a function or persist it as a table. And we do ship some of them. Let's see how many. There's a system table called table engines. That's quite convenient. And we have 55 of these table engines. That's also the beauty of open source, is that people keep adding these table engines. Some of them are actually for storing data, like merge tree table is our like flagship table, the one I used in my previous example. There's like some of them are like replicated versions of it, but here you see that a vast majority are integration engines, like SQLite, like Postgres, NATS, S3, Kafka, you name it. Usually we have already what you need here, from data lake formats like Iceberg, like Delta, to like proprietary or open source data stores. This is pretty much good. So now you have this ability to talk to other systems. And then what you need next is the ability to talk to the systems in the formats they support. So that's the other thing. It's like when you travel, you need a plane to get there, but you need also to speak the language to talk to people. So same thing here. We have a table called system.formats. There's 96 of them in ClickHouse, from JSON to Avro to you name it here. What we have, ORC, Prometheus format, MySQL wire format, protobuf, XML. That's a pretty extensive list. So usually you find what you need in there. If you don't find it, please let us know. We try to implement it, or even better, submit a pull request and we'll review it for you. So these are the formats we support. It's not only formats, it's also pretty good implementation of drivers for these formats that are usually quite fast and leverage the parallelism we saw in the operations we ran earlier. So let's start with a small example. Who here is familiar with Hugging Face? Have you heard of Hugging Face? Cool, so I don't need to introduce it. And a cool feature of Hugging Face is that it's a dataset store as well. So in Hugging Face, you find many types of dataset. This one here is a Parquet dataset that contains Spotify tracks data. So I'm using a URL table function here to describe this data set. And that's a pretty interesting operation, like describing a remote data set that's not even on the same host. I'll have some HTTP parameters here because there's like redirections involved in that query. But here, in less than a second, we describe this data set. Describing means that we inferred data types for this. So understood the structure, thanks to the Parquet metadata, but also took a sample, went through our inference engine, and we found out that, okay, we have some integers here, some strings, some booleans, some floats. That's basically a starting point where you can start querying this data set without even knowing anything about it. Usually it takes some time to model and understand what you need and what you need to represent data. Here we kind of have a shortcut. You notice that all of them are nullable in that case because we cannot assume if there's not null values or not beforehand based on the sample we collect, but you can also decide to control this behavior if you want. So let's see how many rows are in that Parquet file. It's the same query I've run before. Now it's a count, so there's like 114,000 rows in that data set that represent Spotify data, so data about music tracks. Let's see basically what it looks like. Let's do sample of it. Let's do select star, and let's set a limit to 10, and let's do also some kind of magic here that displays the format as vertical format. And if you use MySQL, it has the same capability of displaying data as vertical format. So you see here, artists, album name, track name. What do you expect from a songs data set, basically. You have durations, but you have some very interesting notions here, like energy, loudness, speechiness. I don't even know if these are like correct English words, but they carry this concept on a scale from 0 to 1. They try to kind of rate based on some heuristics this aspect. My favorite one is danceability, and it basically between 0 and 1, it tells you if it's a music you can dance to or not. When everyone agrees that not all the music is something you can dance to. Yeah.
Sorry, so like it's great to have like multiple engines there. How do you like manage building? Like their data models are all different, right? Like for example, MongoDB and you also support Kafka, or I don't know, like
yeah.
How do you like manage them, or so what are the how do you like guarantee consistency, or maybe you don't care about the consistency, or you know?
Yeah, so one way to do it, you mean in the inference engine, or after that, like when you query and you start to join like heterogeneous data sets?
Or the insert to MongoDB, or you just select from the MongoDB? Or?
Yeah, it depends on the table engine. Some of them are bidirectional. You can read and write back to the systems, like the Kafka table engine, like Postgres, for example.
Yeah.
And some of
MongoDB table, and like you can run ClickHouse on top of it, or you need to create a MongoDB table from the ClickHouse interface, then you can use it.
I think of it as foreign data wrappers in Postgres, for example. So you have this like virtual table in ClickHouse that's basically a connectivity hook to the distant MongoDB instance. We can use their types directly. You can be imperative with the types. You can like decide to specify the types, or you can use our inference engine if you want. And in that case, we'll try to find the most convenient type for you. It's not always possible, depending on the samples we're getting. And then it starts becoming interesting if you start like joining two different data types from two different heterogeneous data stores. What we try to do is to find a common data type that's like a superset of this like leaf data type, so that we can support this operation. Again, we try to do a lot of magic so that users have like a useful experience, and like data scientists working on that do not like bang their head on the screen for hours finding the right data type. So we try to help, but keeping in mind that it's not always possible. Sometimes data is not suitable for that. Sometimes you need to specify a schema for it to be efficient. Again, this schema is inferred, but sometimes there's a better way to represent this data. We have enums, for example, that use a lower memory footprint, that are better to use, obviously. We don't do this type of optimizations automatically, I guess. All right, let's check the danceability. So I have an interesting query here that basically queries the same data set and try to find the distribution of tracks by danceability in buckets of 0.1, so between 0 and 1. And we try to see basically in that data set how danceable it is, right? 100,000 rows, it is fairly danceable in my opinion. So, right, you have 0.6, 0.7 are the main values, so it's skewed towards the top. So yeah, it's a pretty good data set if you organize a party or something like that. And that's how basically we leverage data to organize parties at ClickHouse. Now let's do another type of analysis. Also, what's pretty cool about this query is this bar function that displays kind of ASCII bars in terminal. I love using it because, I don't know, pretty proud of this feature. Another one is called the spark bar, which is like a derivative of this bar function, but you'll see how it works. In that case, we are focused on the distribution of durations in the same data set. So we will draw a spark bar of duration per type. So again, it's an OLAP database, so very fast aggregation queries and group bys. And you see here, for example, acoustic songs tend to be quite short, where techno songs are pretty long. I guess it's easy when you loop on your computer, but you haven't heard me saying that. You have also children's songs, for example, that are very, very short, and I guess that's due to their attention span as well. And All right, that's how you use these functions to interact with the dataset that's not even on ClickHouse at the moment. It's still in Hugging Face service. All right, Hugging Face is a public dataset. So sometimes you want to work with datasets that are not public, provided by your users, by yourself, by customers, who knows. And in that case, you can use S3, for example, an object store. I have another example here. It's a query that queries an S3 bucket in EU S3 containing trips data, which is the famous New York City trips data with taxi trips from 2015. So here it's a real test of the hotel connectivity if you're getting good connectivity to S3. And not bad, 9 seconds with the poor Wi-Fi, that's pretty good. And these are like trips data from S3. So what you can do with it is leverage also this inference scheme to make ClickHouse create the table for you without even providing the schema. So that's pretty cool. So we have a create table here, but we haven't provided the schema. We said, this is an empty one, but derive the schema from my select query here. So it will take some time depending also on the connectivity performance.
What assumptions does it make to infer the schema from the data?
Yeah, it's based on a sample we take from the data, and then there's an inference engine with like predefined heuristics that decide that. It's not like any like learned model or anything. These are hard-coded heuristics per data type. And by default, for example, we assume that all of them are nullable, even though it's suboptimal in ClickHouse to declare nullable for sparse indices reasons. But we cannot do much more than that in automated fashion. But that's like a handy shortcut to start working with your data. And then after that, you can just specify a more strict and more representative schema. So here, let's do the show create table for trips. And you see that basically this schema I haven't provided. It was inferred and the table was created for me. What we can do now is just insert, say 10,000 rows from this into.
So the column names are provided, right, as part of the file?
These are the header. Yeah, this I haven't said that. This is a TSV file with a header. So it's called tab separated with names, and it's compressed in GZ format. So again, part of the huge list of data format we saw earlier, we can work with compressed data in tabular formats or any format you want. Here I just told ClickHouse except a TSV file with headers.
And you infer the data types, right?
Exactly. So here we inserted it, and yeah, now we have the trips data locally on my table, and I can do like a select star from trips. Let's do limit 10 and my small vertical thing, and here, yeah, now it's local and it's way faster than working with the remote. You can think of it as basically a step in your data science workflow. You start discovering on the remote service, but at some point you prefer working on data that's local.
And can you change the architecture or the configuration of the table if it turns out data is not exactly what the sample was? So let's say you created a column that is an integer, and then it turns out that it was a string. Can you change that, and how much overhead did that create?
It's a bit tricky to do it. There's like alter table commands that we support. You can like remove, drop, or add columns, but then it will take place from the moment you did it. So you need to insert data, right? Or reinsert this data. And it's fairly common in OLAP stores because we don't have the notion of like rollback or transactions or things like that. So that's very fast, but we kind of hide away some of the OLTP constraints. Yeah.
So there's like some, is it accurate to say there's some pathological case where like you happen to get a bad sample and then it crashes because it's like, oh, I thought this was an int.
Yeah, well, it won't crash. It will basically, we ingest data by block, it will reject this block. And then you can basically decide how to deal with that. There's strategies around that are fairly established. An interesting one is that we introduced a new data type called JSON, which is like a JSON object data type. And this one is interesting because we don't really know what will come in the JSON object. We use the same inference. So you can declare a JSON column if you don't know what to expect. Your data can change in every document if you want, but we will still store it as JSON. It's still fairly young, I guess, in our implementation. It's still labeled as non-prod ready. But this JSON data type, I think, will solve this problem, right? If you have, I don't know, you are subscribing to a RSS feed and you're getting this data, you don't know what it looks like. My recommendation is to use like object. Then, yeah, for ClickHouse, it's an object, right? it's easier.
And it's also like, I'm curious, the columns that you choose by default, right? Do you choose the more specific or the most general? Because it sounds like it's better to go for the most general possible, right?
Yeah, we do choose the most general.
Okay.
Yeah.
If your sample is only integers, maybe it doesn't hurt to use floats. See what I mean?
Oh yeah, but then it's when you start entering like things that are suboptimal, and yeah, I'm not really sure about the type of heuristics. I can look that up. It's also the beauty of open source. You can also look that up in the repository if you want. But yeah, we try to generalize. It's also based on the sample size. You need to remember that, and you can control the sample size. You can decide, okay, I want to do it on the whole table, or I want to do it on 10,000 rows, and I expect that it's a significant sample. All right. That was for like data from Hugging Face, data from S3. Let's talk about OLTP data that's in Postgres, for example. So we have friends at ClickHouse in a company called Supabase. They basically provide managed Postgres services. This is their website. They have it's like completely managed Postgres, and they have this nice interface and this countries table that I want to use. So what I can do is back to my ClickHouse, create a kind of foreign data wrapper here, which is a table engine in PostgreSQL, providing the credentials. You don't have always to provide the credentials in line. You can store them part of what we call the collection in ClickHouse if you don't want to have problems with your security folks. But that's how basically you declare a table. And now that I have this remote Postgres table engine, and I can, Postgres, and I can access my data. Let's do vertical format as well. And here I'm querying Postgres from ClickHouse. This is very useful, especially that there's no ETL involved, there's nothing here. Keep in mind this data is still in progress. It's needed in Postgres, it's not in ClickHouse. So I can decide to load it like we did with S3, or I can decide to just work with it straight away. So what I can do is, for example, do a small join here. I have an example of the join with local data in ClickHouse. So these are like the first 20 numbers. And joining that with the ID column that I'm getting from the countries table. And here I have the first 20 countries. Again, all of this is mixable, even though these are heterogeneous systems, not always similar data types, but somehow compatible data types. So a lot of magic is happening behind the scene to make sure this is streamlined for the users. Again, at this scale, like 20 rows, we're not really doing analytics. So let's try to ramp that up. Let me create a table named Hacker News. I provide the schema this time because I want to have a little bit more control. So I can say, okay, this is an array of unsigned integers of 32. This is string, this is etc. So here I have a little bit more control. This is an empty table for now. And let us read the data from disk. So let me just split my screen here and find a Parquet file that works with this. I have this hackernews.parquet. Let me just copy it into the user files folder. By default, we try to protect the access of the binary into your file system, so it can access only data inside this user files folder. So okay, this is a 6.6 gigabyte file, and let's try to insert it. Let me do something while we do that. Okay, let's run htop. By default, we use half of the available cores, just to, it's like a safe assumption to see that people are doing something else with their box. But let's override that and set max insert thread to 8 and insert data from my Parquet file, 28 million rows in that. And I'm doing it at a rate of 2.5 million rows a second, writing to disk and using every single core of this laptop. And we're done, right? So it took 13.8 seconds to ingest 28 million rows. If you don't believe me, we can do a count query. All right, 28 million, that's good. This is not the type of queries you usually run in analytics. You run group by queries, and here you see that I think everyone is familiar with Hacker News. It's like a online forum where people talk about tech, and here there's like mostly comments, then stories, then polls and job announcements, etc., etc. All right, we've seen many things so far. For the rest of this demo, I'll switch to the cloud version of ClickHouse because I need better connectivity capabilities to work with that. So the hotel Wi-Fi is nice, but yeah, let's do something different. Let me just copy this. And let's move to ClickHouse Cloud. So the difference with ClickHouse Cloud is it's still the same binary we run. The only difference is that it's provided with the whole experience, like user management, a UI, which is the SQL console. But most importantly, it's backed by S3 storage. It's not backed by local disks anymore. So we implement the full separation of storage and compute in that model. And it's pretty cool. We just released actually a blog about how we implement this. It's called Shared Merge Tree. It's a new architecture we designed specially for ClickHouse Cloud. You can think of it as our like fully-fledged separation of storage and compute. And with that, you get many things. You can operational flexibility. We can scale out very easily, add more nodes when we need them. And data is only stored once in S3. And we do some trade-offs, obviously, but it's still very, very performant. So I have the same Hacker News data I saw earlier. This data contains comments, posts, like everything you expect from there. Let's see what basically is there. Let me ask this. Give me a breakdown of rows per month since the beginning. So this is our implementation also of like GPT query generation. And we kind of generate this query for you. You don't have to know all the table functions by heart.
Are you using ChatGPT to do the translation?
Yeah. So in here, we can have now this breakdown. These are like all my entries in the 28 million data set. Let's visualize that in a chart. Let's do month in the x-axis, row count. No, we can see that Hacker News is more and more successful. And apparently something happened around January 2021. But we have also some outliers. We have data from 1970 here. It means like it's not set, basically. And usually that's where you start like cleaning your data. Another big theme of the poly stores. And how do you clean data in ClickHouse? You clean that with jobs that are continuously processing data that you insert, and we call that materialized views. So don't be shocked. That's how we do it at ClickHouse. We kind of rename a little bit the conventions. So I create here a table called Hacker News Filtered. It's empty for the moment. It's just a table that will receive, well, a projection, so a subset of the fields. But let's see, basically the job we'll declare on top of it is simply a SQL query. Make sure I copy everything. So it is a SQL query that selects a subset of the fields available and also remove fields that have deleted equals 0, that are older than 2005, and that doesn't have authors. So if I create this, we have now a materialized view, but you'll notice that it is empty. And for this to work, you need to ingest actually data. That's how basically we do it. It's a live stream. So let's re-ingest the data since it's pretty cheap to do. Let me truncate Hacker News and reinsert everything. So this time not from my local file system, but from an S3 bucket. And here we are reinserting 28 million rows from S3. I see that Hacker News here is still empty. Let's see. We treat data by blocks. So at some point, we'll start seeing the first blocks that are available for us to use. Oh, we have already 2 million rows. And the filtered view gets a stream once it processes the first block. So let me just refresh this. You can either access the row table, like the filter, or now we have filtered view of it, and we can run the same query, and you'll see that all of these are better formatted. They don't have the same data quality issues we saw earlier. All right, a bit over time, so I'll try to go real quick with the last step. So that's pretty nice. We worked with a lot of static data sets so far. Hacker News data is flowing. I can see For example, let me find my query here that I ran earlier. Oh, I dropped it. All right.
Is the GUI exclusive to the cloud version, or?
There is a UI in the open source version as well, but it's like a basic experience. This like with generative LLMs, with the GPT implementation, everything is exclusive to cloud, right? Because we kind of handle your experience in here. So this data, let me ask GPT something. So give me the boundaries of Hacker News. All right, seems pretty okay-ish to me. All right, so 2017, the malformed data until 2021. So let's now do it with the filtered version. It's better, 26 to 2021, so we have a better data set to work with, but still, it stops at 2021. And a lot happened in Hacker News, or still happening every day. So what we can do here is get a live stream for Hacker News. So I prepared a Kafka topic, it's on Confluent Cloud, and this Kafka topic is basically putting an RSS feed and pushing it as Kafka. And here I can just go ahead. Let's call it Hacker News Comments Live. These are my credentials. That looks good to me. This is my broker. And this is like a kind of assisted experience. My data is in JSON format. My topic is named HN Comments. So I have a sample here. And we can see here that we are pulling this from Kafka. So looks like we have live data. It's from 2023, so that's better. Someone is seeking work in Dresden, Germany. Cool. Now we can do also some transformations. You can either pick an existing table. So here I can pick Hacker News and then map my fields from Kafka to the fields in the existing table, or just give it a name. Let's call it live HN. Select a sorting key here. Let's pick ID. This feed here, colon, look redundant to me, so I'm gonna just drop it. Looks good to me. Oh, date is not a string, please. Don't do that. All right. And I'll pick another type of engine here called the replacing mergery. It's just something to avoid duplication. So it will replace or collapse kind of the fields that have the same ID. And next step, you decide how to deal with errors, and that's it. We have an active job that's pulling constantly from Kafka, reading data in real time, so we are registering it right now, successfully created the Click pipe, provisioning it. There's some agents that are running in ClickHouse now, constantly looking for updates from Kafka. You can control how these updates are managed. So this is data from the source. Source here is the remote Confluent broker. And this is data in the destination table. We already have data in destination table, so that's interesting. Let's view this data. And we already ingested 19,000 rows of data from 2023. All right, with that, I think we saw a lot of the capabilities of ClickHouse. We ingested data from object stores, from local files, from Hugging Face, which is using URL table function, from Kafka, from Postgres. All right, so that's a lot, but you can do more, and it's not limited to that. So if you don't find your happiness in that list, please help us extend it. Interoperability is very important in OLAP scenarios because you never know, basically, in your organization what you're getting, and you want to work with data that's basically relevant. And we call this concept time to insight. So if you spend like a week wrangling around with data, and it may be too late for your insight, but thanks to these capabilities, you can do it in a way shorter time frame. Thank you very much for listening to me, and I'll be happy to take any questions.
Yeah, thanks, Ryadh. So, do you have a question? Yeah.
Nice talk. For your natural language SQL query, do you do any error correction or repair?
Oh, that's a good question. You mean GPT-based error correction? Let's do it. Why not? Let's introduce an error. I don't know, max E is not a function I know. And let's see. Let's run it. Oh, this is not a query. Let's fix it. All right, we have a diff here. Let's put it here. Yeah, that looks good to me. Let's apply. And now we have a working query. Yeah, we do live query correction, and sometimes it's based on syntactic, like components like we did. That's fairly easy actually, but sometimes it's also based on our knowledge of the user schema and what we inferred from the remote data sources. That's actually a lot of context we give to the GPT instance in that case. Thanks.
Do you have another question?
Do you happen to know anything about like the way query optimization works with external tables?
That's a very good question. So I have to say that it's not the same for every table engine. So the way it works is that some table engines are pretty naive and they will not implement any optimizations. They will just like push everything to this destination system, and the destination system apply its own heuristics and get back to us. But we have some implementations. For example, the MySQL table engine is smarter than that because we know that we have better aggregation capabilities in ClickHouse. So instead of like pushing some aggregation to the destination MySQL systems, sometimes we ask for some raw data, some raw intervals, and pull that into the server. It's the reverse of predicate push down. It's like, yeah, and we roll up everything at the server side, and we have some benchmarks that show that we are way faster than MySQL in that case, just because we're not trusting MySQL for its analytics capabilities in that case. So I have to say that it's not the same experience depending on the table engine you use, and some of them are more advanced than others, but it really, that's also the kind of beauty of open source. It's basically completely organic. People had this requirement in the MySQL space, and we implemented it, or they contributed it, but our MongoDB users didn't have this requirement to access like document per document, and it's fine for them. These are like lookup tables or something. So it's more naive in terms of implementation.
Thank you.
All right. So let's.
Last question. So thank you for the talk. So for the, I would say as ClickHouse, as an OLAP system, highly parallelizable, use all the CPUs, as you showed us, it's like dozens of millions of data points per second, so that's great. My question is that, doesn't that come at the cost of, basically, you're really efficient at bulk loading, but if you don't do bulk loading and you're inserting data points, like, I would say, gradually or by batch or point by point and so forth, then I would say the merge tree would kind of suffer because you would have a lot of, I would say, stuff to merge, and that will create overhead both on the CPU and on the memory, and also that you would basically. My question is the following: is there a way to use the benefits of the bulk loading in the, say, stream applications or the batch insertions?
All right, that's okay. For the first part, you're completely right. We are obsessed with performance in the OLAP scenario, so we sacrifice things, obviously, for the sake of speed and ingest capacity. Our new like shared memory in cloud with separation of storage and compute. Last week we've been running tests, and we do like 800 million rows a second on a fairly small setup, fairly easily, but it comes at a price, right? Operations that are like granular, access row per row, are not that great. If we get the data ingested row per row, then we generate more parts, then we have more merge operations, then it's also suboptimal. So what we try to do is close this gap, but not with the universal answer. So our goal is not to become like an HTAP system, like an ultimate HTAP. We still on OLAP, pretty much focused on OLAP store, but we fill that functional gap feature by feature. For example, insertions. We provide a capability called asynchronous insertions. With asynchronous insertions, it's like having your own Kafka queue inside ClickHouse. The server itself queues, creates a buffer for the user that's transparent, and then writes the data once there's enough data to write, or once the cadence has kicked in. So that's how we dealt with it on ingest time. On lookup times, we have other approaches. If your data is, let's say, you are using lookup tables, we provide you with another data structure called dictionaries that relies on smarter data structures underneath to perform that. So we believe in like specialization by use case, but we don't believe that we'll be ever like the generic data store. I don't think it's something we are after, but we try to make sure that users are happy. Again, it's an open source software, so it's really like purely organic. like people are using this, they find like limitations, they raise issues, they submit pull requests, we review them, we make sure the implementation is sound, and that's how we grow.
All right, let's thank the speaker again.
Thanks, everyone.
Great talk.